Hi, everybody. Hope you're doing well. Hope you're staying healthy. Um, the next big thing to talk about that's going to carry us through the rest of the semester is to understand how planets form, where they come from. Um, we've been talking so far this semester about observations of stars. We've been focusing mostly on stars lately. Um, But now it's time for us to pivot into the big topic that's going to take us through the end of the semester, which is understanding planets. And we've already talked about the motion of planets and how planets orbit the sun according to Kepler's laws of planetary motion under the influence of gravity. And that's a huge step. That's a huge um, clue that gets us to understanding planets. But we're kind of dancing around the big issue. The big issue is, where do they come from? How do planets form? How do they happen? And that's the big goal for this week, is to say, what kind of a theory can we come up with? What kind of an explanation can we come up with to explain how planets form? And before we get to that, that'll be the next lecture. But before we get to that, um, I want to do a quick introduction. I want to do a quick overview of what does our solar system look like? What do we find in our solar system? What are the trends? What are the patterns in the behavior of our solar system? Because if any good theory to explain our solar system should be able to explain why our solar system looks the way that it looks. So before we can come up with a theory to explain why, we need to talk about the what. What do we see in our solar system? What do we observe? What patterns are there that our theory should be able to explain? So that's what we're going to talk about right now. Okay. Um, what is the solar system? Well, the solar system, as it was originally conceived of, was the sun and the planets going around the sun. So before the invention of the telescope, the only planets that anybody knew about were Mercury through Saturn, and then the moon. And that was it. Before the invention of the telescope, the only things in the solar system that anybody knew about were the sun, the moon, Mercury, Venus, Earth, Mars, Jupiter, Saturn. Once telescopes got invented, though, then you could see you had the superior light gathering power, you had the superior resolution, um, magnification, all those things we talked about when we talked about telescopes. And so you can discover that there are more things in the solar system than just the bright stuff that's really easy to see with the naked eye. When you have the superior optic, what did I do? What happened? There we go. When you have the power of a telescope, though, you can notice that there's a lot more things in the solar system than you can just see with the naked eye. Telescopes were invented in the early 1600s, and so when Galileo bought one and started looking at the sky, one of the first things he discovered was that there are moons around Jupiter. Um, there's a lot of moons around Jupiter, but we'll talk about that in a couple weeks. But Galileo discovered that Jupiter has 4 large moons around it that you can see even with the little telescope that Galileo had at his disposal back then. 40 odd years later, Christian Huygens discovered that there's a large moon around Saturn named Titan. In 1758, William Herschel, I'm pretty sure, discovered Uranus. Right? You can't see Uranus with the naked eye. Uranus is a large planet, but it's also really, really far out there in the solar system. You can only see Uranus with a telescope. And this was huge news. Let me not downplay this, right? The discovery of a new planet was huge because all of the other planets up to this point, Mercury through Saturn, people had known about for thousands of years because you can see them with the naked eye. Everybody can see, like, oh yeah, there's Mars, there's Jupiter. But the discovery of a whole new planet out there in the solar system was a massive discovery. It was huge news. Not only is there one new planet, but Uranus is about twice as far from the sun as Saturn is. So not only is there one new planet in the solar system, now all of a sudden this whole solar system is twice as big as anybody ever knew it was. So this was giant. And this really starts a gold rush because, hey, if there's one new planet out there in the solar system, why not more? So now anybody that has the means to buy a telescope or build a telescope, they start doing it. So you've got people all over the world with new telescopes looking for the next new planets to become the next William Herschel, to say, hey, I also discovered this new planet that has been there the whole time, but nobody ever knew it existed. And in the process of looking for new planets, the first asteroid series was discovered in 1801. The next year, the next asteroid was discovered, and Vesta, I believe, was the second one discovered. They were looking for planets, but in what they ended up discovering was the asteroid belt. Ceres, Vesta, all of these, the first asteroids that were ever discovered, are all out there in the asteroid belt in between the orbits of Mars and Jupiter. In the mid-1800s, Urbain Le Verrier discovered Neptune. In the meantime, again, I'm jumping forward a lot of time here, right? But in the meantime, all of these people with these new telescopes were also discovering more asteroids, new comets, new moons around Jupiter and Saturn especially. It wasn't until 1877 that it was discovered that Mars had not one moon, but two moons. Mars is really close, right? Mars is the closest planet to the sun. Mars is the closest planet to the Earth during certain times of the year. And it took until 1877 to discover that Mars has two moons. And the reason why it took so long to discover them is because they're not that big. The moons of Mars are significantly smaller than our moon, so you got to have some pretty powerful optics to see them. And then Pluto was discovered in 1930, right? Pluto was discovered by Clyde Tombaugh up in Flagstaff at the Lowell Observatory. And it was the first planet discovered in America, so it was huge news in America. The United States made a big deal about it. And this is, Pluto is very small. It's smaller than our moon. It's very far away. It's past the orbit of Neptune. It doesn't look like much in a telescope. It just looked like a faint dot. And so at this point, this gold rush of discovering more and more things in the solar system kind of started petering out. It kind of started trailing away because now you're just finding lots and lots of really small stuff. Moons, asteroids, comets. Pluto, which they called a planet, but we don't do that anymore. But, over the course of the 20th century, people, this inventory grew and grew. People kept discovering more moons, more asteroids, more comets. And this is not trivial. Given modern technology with big modern telescopes and modern cameras, it turns out there's a lot of objects in our solar system. What does a modern inventory of the solar system look like? Well, what do we find? What do we see in our solar system today? We got one star, the sun, 8 planets, Mercury through Neptune, a couple of hundred moons, hundreds of thousands of asteroids, billions of comets, about 1,000 what we're now calling Kuiper belt objects. So a Kuiper belt object is what we call Pluto today. 100 years ago, we called Pluto a planet because, frankly, we didn't know what else to call it. It wasn't a comet, it wasn't an asteroid, it wasn't really a planet like any of the other planets, but hey, we'll call it a planet anyway. As of today, though, we have found about 1,000 of these Pluto-type objects. And so today we don't call them planets, we call them KBOs, Kuiper Belt objects. Look at this inventory. What do you notice? There's this trend. Remember, we're looking for what are the trends, what are the patterns in our solar system? What are the trends that our theory for how the solar system formed should be able to explain? The trend here is, are there more big objects or are there more small objects? What do we see in our solar system? One star, 8 planets, a couple of hundred moons, hundreds of thousands of asteroids, billions of comets. The overall trend in our solar system is that the smaller an object is, the more of them there are. The bigger an object is, the fewer of them there are. And that seems to be true whether you're talking about the really, really big stuff like stars and planets, or even when you get down to the small stuff. Asteroids are smaller than moons, and therefore there's more asteroids than there are moons. Comets are even smaller than asteroids, and so there are billions of comets, whereas there's only hundreds of thousands of asteroids. When you look at all sizes, this trend seems to be consistent. The smaller something is, the more of them there are. Why? Our theory should be able to explain that. Right? When you look at the planets, what you notice is, well, there's 8 planets in the solar system. There are the 4 terrestrial planets, Mercury, Venus, Earth, Mars. And there are the 4 Jovian planets, Jupiter, Saturn, Uranus, Neptune. Why are there 2 types of planets? That's an interesting question, right? There are the 4 terrestrial planets, like Earth. In fact, that's what the word terrestrial means. Literally, it means like Earth. And there are the 4 Jovian planets, and the word Jovian means like Jupiter. Why? Why aren't all of the planets the same type? Why aren't they all similar? Why are there 2 types of planets? And for that matter, why are there only 2? Why aren't there 3 types of planets? Why aren't there 5 types of planets? Hopefully, our theory for how the solar system formed should be able to explain that too. When you look at the terrestrial planets, what do the terrestrial planets have in common, right? When you look at the 4 terrestrial planets, Mercury, Venus, Earth, Mars, okay, my apologies, guys. I need to figure out where to put my face so that it's not quite in the way. I'll go over here. How about that? My apologies. Each of the terrestrial planets is unique in certain ways, and we'll get into the details of that next week about what are the details and what makes each of these planets unique. But for now, let's look at the overview. Let's look at the big picture. What did the terrestrial planets have in common? And actually, when we do start talking about the terrestrial planets in detail, I'm going to lump the moon in there too, because the moon has a lot in common with the terrestrial planets, especially Mercury, and you can kind of get a sense from that picture right there. What do they have in common? Well, the terrestrial planets are small. They are low mass. What are they made of? What are terrestrial planets made of? They're made of rock and metal. And since they're made of rock and metal, they tend to be dense. They orbit close to the sun, right? They all orbit closer to the sun. And since they're closer to the sun, what are their temperatures going to be like? They're going to be hotter. Since they're closer to the sun, are they going to have longer orbital periods or shorter orbital periods? Are they going to take more time or less time to orbit the sun? They're going to take less time. So, why? Right? What is it? Why do all the planets that orbit near the sun, why do they tend to be small, dense, rocky, and metallic? hopefully our theory for how the solar system formed should be able to explain that. If we... Now I can get out of the way here. If I sort of draw a cartoon to show you a map of the solar system, here you have. Here's the orbits of Mercury, Venus, Earth, Mars, all orbiting close to the Sun. Fast orbital velocities, short orbital periods. Once you get out past the orbit of Mars, you're immediately out there into the orbit of the asteroid belt. So not all of the asteroids in the solar system live in the asteroid belt, but most of them do. Most asteroids orbit in the asteroid belt. Several 100,000 of them. And then right out past the asteroid belt, then you're out into the orbit of Jupiter. Then you're in the outer solar system in the realm of the Jovian planets. What do the Jovian planets all have in common? What characterizes the Jovian planets? Well, as you can see from there, they're big. They are high mass. What are they made of? They're mostly made of gas. So typically you also call the Jovian planets gas giants because they're mostly made of gas. And if they're made of gas, what are their densities likely to be? Low density. They all orbit far from the sun. Oh, sorry, but we'll get there back there in a second. But here's my sort of, if we zoom out and I draw a cartoon of the outer solar system, here you have the orbits of Jupiter, Saturn, Uranus, Neptune, all orbiting far from the sun. And so if they're far from the sun, they have long orbital periods. It takes many years for each of them to orbit the sun once. They've got slow orbital velocities, if you think about Kepler's laws. What about surface temperatures? If they're far from the sun, are they going to be hot or are they going to be cold? It's going to be cold. The Jovian planets all tend to have a lot of moons. So not all of the moons are large. To show you Titan and Triton down there. In fact, what's the trend in our solar system? The smaller something is, the more of them there are. So most of the moons in our solar system are smaller, but there are a handful that are big. So here are the sizes of the 4 largest moons of Jupiter, the ones that Galileo discovered with his little telescope. We tend to call these the Galilean moons because he discovered them. These are Io, Europa, Ganymede, and Callisto. Titan is the largest moon of Saturn. Triton is the largest moon of Neptune. Uranus doesn't have any big moons. Uranus has like a dozen moons, but none of them are that large, which is interesting. But there's a lot of weird things about Uranus. So, again, so you can get the sense from this picture that each of the moons is a little different in their own ways. Each moon has a slightly different story to tell. And so in a couple of weeks, we're going to zoom in and look at the moons of our solar system and say, well, what story do they have to tell? How are they different from planets? What can they tell us about the history of our solar system? And the answer is kind of a lot, but we'll get there. Once you get out past the orbit of Neptune, then you're out in what's called the Kuiper belt. And the Kuiper belt is this big loose belt of material orbiting around the sun. This is where you find the Kuiper belt objects, like Pluto. Eris, you can sort of see the dotted curve there, is the orbit of Eris. Eris is another large Kuiper belt object, kind of like Pluto. Out there in the Kuiper belt, you also find lots of comets. So the Kuiper belt is swarming with lots of small stuff. Kuiper belt objects like Pluto, and then even smaller things like comets are out there. So this put myself down. Put myself over here. Sorry, my apologies, guys. Why? Why are there these two types of planets? Right? Why is it that we have these Jovian planets that are large, high mass, gaseous, low density, have lots of moons? They all have rings. I didn't say that. All of the Jovian planets have rings. None of the terrestrial planets have rings. Interesting. fast rotation, and strong magnetic fields, which is also kind of interesting. We'll see if we can't figure that out in the next couple of weeks. And then why are there these terrestrial planets? All of them small, low mass, dense, rocky, not very many moons. Earth has 1 moon, Mars has 2 moons. That's it, as far as moons orbiting around terrestrial planets. Why is that? Maybe our theory for the solar system can explain that. And all the terrestrial planets orbit close to the sun. All the Jovian planets orbit far from the sun. These are a hell of a lot of coincidences, if this is a coincidence, right? We've got 4 terrestrial planets, 4 Jovian planets. They all have these properties in common. That's a trend. That's a pattern. And if we're going to come up with a theory to explain how our solar system formed, we should be able to explain that. What about the asteroids and the comets? I keep talking about them, but what are they? Well, asteroids are essentially big rocks, so they're like mountains floating around, orbiting around the sun. A typical asteroid's between 1 and 1,000 kilometers in size. Most of them are orbiting in between Mars and Jupiter out there in the asteroid belt, although not all of them. Comets are mostly made of ice, and they only get to be between 1 and 100 kilometers. So that's the big difference between asteroids and comets. Asteroids are mostly rock, comets are mostly made of ice, and your typical asteroid is larger than your typical comet. And because comets are smaller, there tends to be more of them. Okay. Here's what a typical asteroid looks like. This is asteroid Ida, taken from up close a few years ago. Lumpy, irregular, about 53 kilometers in length. So, 50 kilometers. That's a big mountain, essentially. Just a giant rock orbiting around the sun. This is a close-up picture and a faraway picture of comet Hartley 2. The typical concept of a comet is this big, the big glowing head with the big tail going off this way. That's what a comet looks like when it gets near the Earth and when it gets near the sun. When a comet is far from the sun, it mostly all you can see about it is the frozen icy part. So this is the solid icy center of the comet. It's only when that comet gets close to the sun, what happens to ice when you heat it up near the sun? The ice melts and vaporizes, and so here you can even see the picture here where the ice is vaporizing because it's being heated up by sunlight, and then when all that vapor blows away from the ice, it blows out into this big fuzzy gaseous head, and the gas streams away from the comet as that tail. So when a comet gets near the inner solar system, near Earth, near the sun, it looks like the usual cartoon that we think of a comet looking. But when a comet orbits out far away from the sun, where it's cold and it's dark and there's not a lot of sunlight to melt the ice, it just looks like essentially a big iceberg. Just a big chunk of dirt and ice orbiting the sun. And then you get out there in the Kuiper belt. And the Kuiper belt objects are a very new hot topic of research, because Pluto was discovered almost 100 years ago, and Pluto was always the weird oddball, right? We called Pluto a planet because we didn't know what else to call it, but Pluto was really its own thing. It was unlike any of the other planets, right? Because Pluto is small. Here's the relative sizes. Here's the size of Pluto. Here's the size of Eris. I mentioned that a minute ago, relative to the moon, right? So Pluto is tiny, but it's also orbiting really far from the sun. So it's not quite a terrestrial planet. It's not a Jovian planet. What do we call it? I don't know. Well, we called it a planet. For the better part of the 20th century, we called Pluto a planet, even though it wasn't like the terrestrial planets and it wasn't like the Jovian planets. So we'll just lump it in and call them planets, even though it doesn't really make sense. Right? Starting in the 1990s, though, then we started finding more of these Kuiper Belt objects, like Eris and Quaoar is this one down here. Pluto has a large moon called Charon, which is, I mean, Charon is almost the same size as Quaoar is, so actually it's not quite fair to say Charon is the moon and Pluto is the planet, not a planet, planetoid, planetish thing. It's actually more like, it's more realistic to say that Pluto and Charon are binaries. It's two Kuiper Belt objects orbiting around each other. Because if you watch them, when you watch Pluto and Charon over the course of several hours, you can actually watch them orbiting around each other. It's not like one is standing still and the other one's going around it. They're actually orbiting around their common center of mass. So each of them is, in a sense, a Kuiper Belt object. And then there are this illustration I picked because it looks nice, but it actually is a little outdated because Pluto, in the last few years, we've discovered that Pluto actually has 5 moons, if you want to call them that. So there's the big one, Charon, and then there are 4 tiny moons also orbiting around Pluto. They're called Nix, Hydra, Styx, and Kerberos. And if I can find a pretty illustration that actually shows you all 5, maybe I'll have to do that and update these slides, but for now you get the idea. Here are the sizes of the 4 largest asteroids in the asteroid belt. These are Ceres, Vesta, Pallas, and Hygeia. These are just the 4 biggest, right? Most of the asteroids are significantly smaller. And then Comet Hale-Bopp is sort of pretty typical. This is the typical size of a comet nucleus. The nucleus is the frozen part, right? If you can see through the gas of the big head and the big tail, the frozen solid part of the icy frozen part is what's called the nucleus.